Hello again, folks, in 114. Today we're covering section 12.6. Here is the calendar to corroborate here. Okay. Yep, today is Monday the 26th. So we were covering section 12.6. I guess that's appropriate, right? 2.6. Okay. So we are nearing the end, closer and closer. Right. The packet I have here today is hefty, actually, but I'm going to start with that diagram that I use for my own sake, which is just to capture the vocabulary first, and any symbols that may be relevant. We'll do that. Then I'll draw some diagrams to summarize as well. Here is the actual material that I swiped from the textbook, which is worthy of a read. Relevant stuff. This is especially good. If you're going to print anything, print this. This is a page for scatter diagrams and what they imply. There's a formula at the bottom. Is kind of tricky. This table as well, also very important. Okay. These are critical values. Something that we compare to. And then there's a formula about how to calculate slope and Y-intercept given data. You can use these formulas if necessary. The truth is you'll probably be using a calculator more than anything, but nonetheless. I want one time to sort of walk you through the process of how to do this by hand so you appreciate it a bit more. And I put the same formula from earlier in the packet there. Then there's one diagram to show you how to do a line of best fit by hand. All right. Again, realistically, you probably would do that with Microsoft Excel or a TI-83 or 84 if you were in that class, like stats or calc. All right. More likely pre-calc. Anyhow, then there are the actual examples. We'll spend the majority of time probably going over each of those. And I think that's it. There are 4 examples that we'll go through. But they take a little bit of time. They're intricate, you know. All right, so do print that and we'll go over this. I'm going to fine-tooth comb here. Let me see if I can pull up the projector here. And get busy. Geez, why does that look like it's in black and white? Is it? No, can't be. That's just very faded. Lower than it ought to be. Let me close some doors here. I'm slow today. Yeah, no, it would be great. Don't crash, please. I'm just pulling up a white surface. I just wish it wasn't so small. There we go. Ooh, much better. Okay. All right. Get rid of that. Okay. All right. Section 12.6. is comprised of basically two things. I'm going to move this after I get through. It's a very short diagram. I like to make this diagram in lieu of immediate vocabulary. So let me do this really quickly. All right. Section 12.6 is about correlation. And hopefully this is visible, and if it's not, I'll fix it. It's a bit faint. Correlation and regression. It's also kind of faint. Aside. What is correlation? Well, correlation is about determining if there is a relationship determining if there is determining, sorry. You can see the difference between these markers here. Determining if there is a relationship between two variables, which to get us just rolling, it's usually x and y. And how strong. Okay, so point one here is, again, sorry for the redundancy, right? Determining if there is a relationship between two variables, and if so, how strong. All right, how strong, and this process is correlation. Okay. As far as regression is concerned, this is determining the actual equation to model a relationship. So just to emphasize key phrases here, this is also a process of determining the actual equation, to model a relationship. Okay. Now, if we're talking about x and y, and if it happens to be a linear relationship, what we will resurrect is good old y equals mx plus b, or some some incarnation of this, if it happens to be linear, right, relationship, then that would be appropriate. If you had a more complicated situation, say for example like an exponential relationship, then you would use something that involves e potentially, or base x with a variable as an exponent. Anyhow, you're not responsible for that. You're responsible primarily for linear relationships, right? And these are the two processes. Okay, so we're going to be dealing with correlation and regression, all right? Establishing a relationship, if there is one, how strong, and the model for it, right? The model that describes it. with algebraic equation. Okay. Now, having said that, let me pull up a slide. Losing my voice here. I'll just minimize. I want to get this vocabulary out of the way and then come back to it as we go about the section. Since we're talking potentially about a linear relationship, right, what we'll be concerned with eventually is something called a linear correlation coefficient. Right, which is abbreviated by the letter R, lowercase r. Okay. All right, and basically this is a number, it has a unitless number used to describe strength of, in our case, a linear relationship. Okay. In a very literal sense, just to add some emphasis here, I'll put a little an asterisk. What it literally is a measure of how far a set of data values are or vary from a straight line. Okay. So it's literally a measure of how far a set of data values vary from a straight line. So if something is in fact exhibiting a linear relationship, then on a graph, there might be some data values that look like this, maybe slightly zigzagging, but not too bad. And then what we would establish is a line that basically predicts these. Right? Any one of the values, right, is either on the line as part of it, or it is some distance from the line. So the line of best fit, which will be established later, is something that would be perfectly smack in the middle of this trail of dots, if you will. Right? It won't be on top of every single one of them, but it will be the ideal as close to the ideal as it can be to describe a linear relationship. Right? And that's what we need this value R for. All right, the linear correlation coefficient. to really establish where that ought to be, or if it even exists. Okay. Here's another point to add to this. All right. Still pertaining to this. Essentially, the more the data stray from the ideal line used to describe them, the weaker the relationship. Between the two variables. X and Y, or whatever is actually being discussed. Because you could change the label, remember. And the closer to 0 R becomes. That definitely warrants a little bit of reiterating here. I'm dedicating an entire diagram to this one word, but it really deserves it. Okay. The more that the data stray, right, that is the dots that make up a line, if they're very far apart from the ideal line. The weaker the relationship between the variables X and Y. It won't be, in an obvious way, sort of trending a certain direction. It'll look just like a bunch of, dots thrown onto a page. The weaker the relation, and the closer the R value becomes to 0. Right. So if you had no diagram at all, you just had the numbers purely to stare at, R equals some number, all right, you'll see that it is very, very close to 0 if there is no relationship at all, right? Just to dig through the packet just a wee bit, here again is what I was talking about. All right, this is a very nice overview of what are called scatter plots. Scatter plots are data values that are graphed onto a coordinate plane X and Y. Remember, if it's something practical, it's usually just quadrant 1, as you see in each of these cases, rather than the whole cross shape. Anyhow, this first graph is something that has a strong positive correlation, right? Meaning it's trending upward in this direction, and things are very much aligned in an obvious way, right? These are aligned, right? Maybe tilted a little bit, but it doesn't matter. All right, these are aligned, however, they're not quite as aligned as you see in this first scenario. And as we go across the page here in description, different examples, they get less and less like an actual genuine line and more like a random cluster, it seems like. All right, when you get to a situation like either one of these two, you could say that there is no correlation, or it is at best weak. Those are positive relationships. Right? The R value here would be 0. The R value here would be probably 1, something like that. You could also have negative relationships, which I think is a little bit misleading, because when somebody hears that, they go, oh, that means it doesn't have one. Not necessarily. It just means that it's tilted in a different direction. All right. Now, as you see, this is sort of projecting upward from left to right. If you have an evidently aligned bunch of data, but they just happen to be pointing downwardly from left to right, you say it is a strong relationship, but it happens to be a negative correlation, right? And as you go across to the other examples, you can see that it gets more and more random and less deliberate. Okay, so you definitely want this page because it helps you understand what this is really referring to. There is a graphical way to analyze whether there's a relationship, and then there's a numerical way of analyzing that relationship. Okay, this is a little bit easy if you just have a number, but this is maybe a little bit more intuitive if you have a picture. I really wanted to put some other things here. I will come back to it. Let me turn this off for a moment and just complete this thought in terms of correlation coefficient. Seems to be heading that direction. All right. Now, oh, that's pretty good. Let me erase this. And draw you another slightly smaller diagram. Delicious blue. Alright. There's something known as the R scale. Let's call it the linear correlation coefficient R scale. All right, where your maxima are either technically minimum, right? -1, and your maximum is +1. So right smack in the middle is 0. Okay, these are values for R. R equals that, R equals that, R equals that, or something in between, but never beyond this. Right. When you have an R value which you calculate, that is exactly 1, -1 in this direction here. And realize that from here to here is negative R's. This is the strongest relationship between two variables, so let's just say between X and Y, all right, but negative. So that means in terms of a graph, here again is a graph, that you have a relationship that is, if it's a bunch of dots headed this way, they tend to be pointing down in this respect, right? So we don't have the second quadrant nor the fourth quadrant in the case of practical math, but from top left to bottom right. If you have something basically projected that way, it's probably R equals -1 or very close to it. Let me turn this light on here. Okay. On the other hand, if you have something on this side of 0, these are positive R's. The actual value, magnitude of 1 is the strongest relationship between, just say for example again, X and Y, but positive. Which again, don't be misled, all right, whether something is positive or negative. Negative people tend to think of, oh, it means it's non-existent. No, not really. Right? If you have a graph of the data, right, the dots would be something more like this, the data values. So your line would be projected upward like this, right? So say from the bottom left to the top right. 1 being like a perfectly straight line. Alright, if you have something that is a little slightly more jumbled, then it will get a little bit closer to 0. Right? If you have the situation where you get exactly 0, right, that means that there is no relationship, right, between the two variables. Okay? There's no correlation. They are not related in any way. Okay? All right. Let's see. All right. Let me give you something of a review about y equals mx plus b. And then we'll come back to calculating r. All right. So I'm going to erase this. Just to remind you of, take out every color here, let's see. Remember, y equals mx plus b. And I'm trying to draw some emphasis to these figures here. I really would do the same thing. Maybe I'll put this in green as well. The things in green are important, but the things that are distinct are y and x here. Okay. Here's a little thought cloud. Remember the equation of a line. Y equals mx plus b. Remember, there's different incarnations of the same thing, but this is the most practical, which is why they usually stress this when you're in high school. There is sort of a math purist way of talking about it, and then there's a pragmatist way of talking about it. So, to summarize, let's look at this from the perspective of a math purist. The perspective of a math purist versus the perspective of a pragmatist. They'll both be talking about the same thing, but the labels will be different. All right, let's start from working all the way from left to right. How would a math purist refer to the y value in a general way? They would say y is, this is in the context of a function, y is the output. Right. How would they refer to Y from a pragmatist perspective? And what do I mean by a pragmatist? Pragmatist is somebody who will talk about this in the context of an experiment, maybe in business. Basically testing a hypothesis. Not to digress, but remember what a hypothesis is. A hypothesis is a temporary answer to a question, right, or an assumption. Right, so in our case, if we assume that there is a relationship between one variable and some other variable, all right, we might write an equation that is essentially the hypothesis, and then we can test it to see if there is genuinely a relationship or not. Anyhow, a pragmatist discusses the same subject from the context of an experiment. Okay, so if we're talking about Y in this context, Y here would be referred to as a dependent variable. I always forget how to spell that. All right. Now, if we were discussing X, X is the input in the context of a function, right? X from the pragmatist perspective is the independent variable. Right. It's basically the thing that is the controlled quantity. Right. Which is why I think input is a little bit more practical, really. But maybe I'm just a math purist. Anyhow, whatever this is going to affect this, which is why it is appropriate to call Y, based upon this arrangement, as being dependent upon X. But it's not solely dependent upon X, it's dependent upon what would be the slope, remember? Slope of a line, and what would be the Y-intercept, right? The B value, all right? All right, now as far as those things are concerned, green, don't let me have green. M, again, math purists speak here, is slope. All right, what does slope do? It's a number that basically affects the incline of a line. Essentially, I hate to use this phrase, but steepness, if you will. All right, slope in the context of a pragmatist, somebody running an experiment, whether it's a science or business or something like that. M is the rate of change. All right, a number that relates we might say converts one unit into another. I'm running out of space here, but when we had done conversion factors, right, basically the conversion factors could be regarded as a slope. But we didn't do any graphing, so I mean, it wasn't appropriate maybe to say that at the time. Now that we're in the subject, deep in the woods here, deep in the weeds, all right, now we can, right? They're really the same thing. It's just looking at something from two different perspectives. So M is a rate of change, right? It's a number, again, usually it's a fraction, right, that relates or converts one unit into another unit. Okay. I'm going to use black just to go for B here, right? Just because I have very limited color set here. But B, from the math purist perspective, I have some paper towel here. B is the Y-intercept. All right, it is literally where a line crosses the y-axis. So if we had, here's a simple graph again, if we had a line that crosses the y-axis, then that would be the b value in the style of a coordinate. So it would be 0, b, ordered pairs. In the context of a pragmatist, I'm just going to make some space here. B is the starting point. Of data. All right, remember, in math world, there's 4 quadrants, right? But in the real world, there's only 1 quadrant. So in theory, in math world, anything is possible. So there could be more data values behind the y-axis, but in a practical sense, that wouldn't exist. So if you had a graph, here again is a very simple graph. Your line would start here. That's still a b value. Again, in the style of a coordinate would be 0b. But there isn't anything behind it, right? This is a starting point. Start at b. Okay? Now as for the labeling, if instead of referring to things as x and y, because we could be more general than that, right? This would be what normally is the x-axis here. This would be the independent axis instead, which is probably better because the variables are not always labeled even to begin with as x and y. And if this is normally y, then we can instead call this the dependent axis, running vertically. All right. Let's see. All right. Let me just throw something. Someone write it down. Sometimes you get some inspiration in the midst of teaching, right? Okay. Let's see. A phrase, just in case it gets thrown around here. And I don't want you to be intimidated. is bivariant data. Right? It's just referring to a situation where you have two variables. If you hear that phrase, bivariant data, it's a fancy way of saying two variable data. Something that has an independent and a dependent variable, or math purist way of speaking, math speak, yx. Yeah. Okay. Let's get rolling here. I think what I want to do is just this one time walk you through how to calculate an R value by brute force. All right. So what I'm going to point you to is we're going to do example 1 here, but I want you to take if you're following along, maybe take this blank table that I have, and we're going to utilize this formula. But in order to set it up so that it's a little bit easier, I want to walk you through the process. So humor me. All right. I have to turn my projector on. Maybe not. Yes, I do actually. Now, firstly, let's look at these examples here. Okay, now here is a table of data, all right? And what you see here is the number of workers absent at some company, and along this axis, the number of defective parts that are manufactured. So somebody is basically testing the hypothesis that there is a relationship between the number of workers absent and the number of defective parts that the company makes. That's their hypothesis. I mean, it's kind of vague right now, right? But they're assuming that this is the relationship. That the number, if this is the horizontal axis, then the number of workers is the independent, I always forget how to spell this. The independent variable, number of workers absent, and the number of defective parts is the dependent variable. So let me get out of the way. In this arrangement. Okay, and this is what they've concluded. All right. When they noticed that there were 3 people absent, that there were approximately 15 defective parts produced. When there were 2 people absent, then there was approximately 20. All right. When there were 5 people absent, right, then there was a little bit more. There was closer to 25. When there was 6 people absent, there was 30 parts defective, right? So even though it isn't a perfectly straight line, as you can see, it's a bit scattered, all right? And this again is referred to as a scatter plot. You can see that there is sort of an intimation, is that the word? Sort of something that is implied here, that there is a kind of relationship. So in order to really certify whether there is a relationship, we need to calculate an R value. R, once calculated, will validate, all right, this hypothesis. Okay, so we're going to calculate the R values, all right, the R value. Okay, now what you see down here, I'm trying to purposely obscure a little bit. Example 1, I'll read this much of it. Egan Electronics provided the following daily records. Don't think for a moment that this is day 1, day 2, day 3. It isn't really. Okay, it's number of people. All right. Provided the following daily record about the number of assembly line workers absent and the number of defective parts produced for 6 days. All right. This 6 that you see here is coincidentally, a day, the maximum number of days, and a maximum number of people. It's just an unfortunate coincidence. All right. Determine the correlation coefficient, the R value, right, between the number of workers, that is essentially the X value here, right, the independent variable, and the number of defective parts produced, that is the Y value or dependent variable, right? So basically what we're going to do is we're going to steal these values that I'm encapsulating here. All right, again, don't get bogged down by the number of days and the similarity in these numbers. 6 days is just a coincidental figure, okay? And to do that, what I'm going to do is just to make it do it one time, all right? Pull up this table that I have as a blank here. All right. As you can see, the formula to calculate is quite involved. The formula necessary to calculate an R value is quite tricky. All right. All right. It's a ratio. This line you see here of these quantities that you see here. I forget offhand exactly how this is derived. I have a sneaking suspicion that the Pythagorean theorem is somehow part of this, because you see a square root. Right. Anyhow, don't dwell upon that. What we're going to do is go through the process, right, of calculating these numbers first, so that we could then insert them in the formula. Just to do this by hand one time. Okay. So I have this somewhat labeled here. Independent, dependent variable. I want to maximize space, so I'm just going to pull it up that far. And let's see, 1, 2, 3, 4, 5, 6. I may have to shrink this. Let's see. Yeah. That's the wee bit. No, don't go crazy. Alright. Whatever I have to, I will move around. Okay. This column that is X, right? the independent column, all right? What is it in the context of this problem? These absent workers. So I'm just going to fill in that little extra description. It isn't imperative, but it might help you get rolling here. All right, what is the Y column, the dependent variable? All right, these are defective parts. Okay, so the data that we have, or that we're borrowing here from example 1, looks like so. Where is it? There we go. The first set of data, ordered pairs would be 3 and 15, and then it would be 5 and 22, and then 0 and 7, 1 and 12, and 2 and 20, it looks like. Pardon me, it's 6 and 30, reading it backwards. No, it is 2 and 20, good. Okay, so, I'm just going to put this here for my own sake. The first point, these are points which technically are days as well, if you want to get technical. I use a different color. Data point, which are technically days. All right. Is this in tandem? All right. 3 in tandem with 15. All right. Now, just to kind of give myself a little bit of space here, to set a good example, I'll draw a horizontal line. And we'll get going here. I left it without the horizontal lines when I printed it because I figured if you wanted to, you could, divvy this up, chop it up for whatever unique problem that you have. In this case, we need 6 of these, so I'm going to have to move something. All right. Now I think I really should back off so you see the whole page here. So we have data point, the first one, which is technically the first day, right? On day 1, there were 3 people who were absent, and as a consequence, they assume 15 parts were defective. Right? On day 2, there were 5 people absent, and there were 22 parts that were defective. Right. On day 3, there were 0 people absent, and yet in spite of that, there were 7 parts that were defective. Right. On day 4 of observing, right, there was 1 person absent, and there were 12 parts that were defective. On day 5, there were 2 people absent, and there were 20 parts that were defective. And finally, on day 6, coincidentally, there were 6 people absent, and there were 30 parts that were defective. All right. Now, Again, if a person is going to calculate this R value brute force, then you really need to tabulate these figures that you see in the adjacent columns here. Right. So we have everything that we need from the tabulated data here. All right. We just established that this is an independent variable, this is a dependent variable in theory. Absentees and defective parts. Okay, so some of this you could do without a machine, a calculator of any sort. X squared is part of the formula. So if it's 3 times 3, then this is just 9, right? If you calculate y squared, it's 15 times 15, which is 225. If you multiply these two things together, 3 times 15, it's 45, right? It might get less and less familiar, and you may have to rely on your calculator at some point, but you're collecting the input values. 5 squared is 25, 22 squared is apparently 484, and 5 times 22 is 110. 0 squared is just 0, 7 squared is just 49, 0 times 7 is just 0. 1 squared is 1, 12 squared is 144, 1 times 12 is 12. 2 squared is 4, 20 squared is 400, 20 times 2 is 40. 6 squared is 36, 30 squared is 900. Right, and 6 times 30 is 180. Now, at the very bottom here, you would need the sums. All right. So if you add up everything in the red column here, what you should get is that there are a sum of x's would be 17. If you add up the blue y column here, what you should get is 106 y. Right? If you add up the x squares column, right, you would get 75. It's really this number that you're going to need in addition to these two. If you add up the y squared column, you're going to have 2,202. And if you add up the x times y, you'll get 387. So having taken the time to take the data, put it in this table, and then do the basic calculations yourself, you now have all of the numbers necessary, right, to fill in the formula. So with that in mind, let me turn this light back on. Move the curtain aside here and turn off the projector. All right. Again, just do this one time just to get a feel, and then I'll show you how to use your calculator. All right. If this is the formula to calculate R, for the sake of validating, right, the hypothesis that there is a relationship between absent workers and defective parts. That's a mouthful. R is equal to number of data values, right? Don't be confused. This isn't asking for the official, like the official formula for a cardinal number, right? It's actually asking you as if this was a variable, so I'm going to wrap a parentheses here. The sum of the xy's, sum of the x's times the sum of the y's, all sitting on top of these figures. And sum of x squares minus sum of x squared as an afterthought. Sum of y squares minus squaring as an afterthought. Okay, because we took the time to tabulate, we've really done the hard part. We're just going to basically set the controls on the machine here by implementing these figures in the appropriate places. All right. The number of data values, six. So I have a 6, 6, and a 6 here. El Diablo. Okay. It is bedeviling at any rate. All right. The figure that would go here, the sum of the xy's, is 387. So 387 would be standing in place of this. Okay. Let's see. Sum of the x's, 17. Sum of the y's, 106. Okay. Sum of x's squared. That would be 75 in this case. The sum of x's, which is already established as being 17, then has to be squared also, as an afterthought. Sum of y squared would be 2,202. So one really yucky number here. And the sum of the y's then squared is 106. Then squared. Right. So what this figure is here, 17 squared, is really 289. And this 106 over here is really 1,997. No, I'm sorry, 11,236. It looks like. Okay. Now, if you're doing this by hand, all right, what you should do is basically simplify all of the top independently right? Then simplify all of the bottom independently. All right, before you merge them. The very last thing that you would do is technically divide because of the line that forms this ratio here. Okay, so if you take the time to basically straighten out multiplying first, multiplying this second, and then subtracting, what you get above the line, all right, is the figure 520. Right. If you then take the time, and this is more arduous, obviously, because you have multiple operations, and then you have square roots. Right. It is unfortunate. All right. And I would, if you had a pretty decent calculator, you probably can do it well on this. Just take advantage of the parentheses as buttons. All right. Make sure that you very anal retentively isolate everything. All right. Because you don't want it to accidentally screw something up. If you don't do that, if you do it piecemeal, or if you have a cheapy calculator, it's going to end up rounding a lot mid-calculation, and then you're not going to get something that's as nice as it could be. So do a little bit of the hard work first, right? When you get to something that is an irrational number, like a square root, all right, kind of reserve that for the calculator itself, because again, you're trying to avoid rounding mid-calculation. So what I'm getting at is that I would work on this, right? 6 times, for example, 75 is 150, right? No, pardon me, what am I saying? All right, it's 450. Right. Carry the 3, 42, 42 plus 3 is 45, good. So, and you already know that this is 289 is what 17 squared is. If you subtract these two things, all right, you end up with essentially the square root of 161. All right, this is something that, again, I'm going to put over here. And the reason why I'm not going any further with that is because, again, it's an irrational number. It's under a square root, and it's not a perfect square. The number 161 is not a perfect square, which means this is not going to produce a whole number. It will be an infinitely stretching decimal. So I'm avoiding some issues. Then I'm going to straighten this out as far as I can go. All right, in this case, 6 times 2,202 is this terrible figure, 13,212. All right, already took the time. 106 squared is 11,236. If you subtract these two things, all right, you will have one number underneath the radical sign. All right. And in that instance, what you should get is this. And I'll put this in a different color. The square root of 1976. Okay. They themselves have not been multiplied yet. All right. This is where, again, even if I were using my calculator, I would reserve it for this point. All right. Basically, what you're going to enter is, this is your top figure, 520. Then you're going to hit the division symbol, and then you very anal retentively are going to use the parentheses. All right, and the radical signs. Okay, when this is really why you would need this type of calculator for this class, all right, rather than some cheapy one, or something better, which in theory would be like a TI-83, but it's a $100 calculator versus a $20 calculator. All right, so anyhow, humor me. Try to minimize the glare here. That's a wee bit better. 520 divided by, there's only one figure above the line, so we're just going to hit 520 and then division symbol. And now I'm going to use two parentheses, 1, 2, all right? And now I need a square root. So I'm going to hit second and then this symbol, all right? Although it's giving me an X, let me just correct that, I'm sorry. Doing things backwards. I'm going to hit second and then X squared just to get that. I could get away with not having this extra parentheses, but hey, whatever. Just because they put one in the formula, so I'll just back off and delete that. All right. And in here I'm going to type the radicand 161, but now very carefully close the parentheses. This is your first radical, and this first parentheses here is grouping this as part of the bottom, not exclusively the bottom. So now I have to put in a second radical here. So second x squared, and then enter 1976. Okay. And now let's see. Close that. That just closes the function input. Sorry, I hurt my finger here. And now to encapsulate the entire bottom, I'm going to put this last parentheses here. All right, so just to scroll backward here, you see there's the parentheses that encapsulates both radicals. This is just the second one. This is just the first one. All right, and that is the parentheses that starts it. Okay, now if all is well and good, this will give us a decimal figure. All right, but like I said, I didn't calculate what this is, all right, because it's an irrational number, and you don't want to have to round mid-calculation. I'm purposely circumventing that. So enter, and here you see it, thankfully. 927852, right? A bunch of, because of the radicals here. An infinitely stretching number, likely. All right. So this is our R value. Having taken the time to go through this, here's what we got. R is equal to 0.92, whatever it is, 921, 927, 852, and that's just up to the edge of the screen. Right, so if we rounded it, say, to about 92, or 3 spaces, you can go to the thousandths place if you like. R is about equal to 0.92. I think that would probably be sufficient for our purposes. All right, I'm only rounding dead last, you see. All right. Now, think about it this way. Here's our scale from earlier. If this is the R scale with a maximum of +1, and a minimum of R equals -1, and 0 right smack in the middle. This is a positive figure, 0.92, which would basically park it right about there. R about equal to 0.92. So if you had to say whether there is a relationship or not, what would you probably guess, right? Since it isn't 0, and 0 represents no relationship. No relation, right? And 1 is strongest positive relation. What would you guess about something that produces an R value of about 0.92? I would say yes, that this has a very strong relationship. Between absent workers and defective parts. Right? We could kind of see that visually from the data from the graph. Right? There is no line yet here, but as you can see, although it isn't perfect, it zigzags just a wee bit. It is basically from the bottom left pointing upward towards, or leaning upward towards the top right. So this definitely would imply that. This is a numerical value to imply that, to validate that. All right. So what could you say? More absent, the more absent workers, right? The more defective parts. Right, that's the assumption one could make. There's one thing I want to go back and sort of fill in on that diagram, so I'll do that now. If this is our R scale, and yes, this is the positive side, and this is the negative side, and this is strongest negative correlation, and this is the strongest positive correlation, and this is to suggest that there is in fact no correlation. One thing I could add to this that I regret not having done sooner is this. In terms of the variables, anything that is in between these two, right? You have an x variable that would be increasing. As the y variable is increasing, right? That is to say, both variables increasing. Left to right. If you have a figure, whatever it is, as long as it's not 0, but something that is in here, as the x variable increases, the y variable decreases. As one increases, the other decreases. All right, reading it left to right. Okay, that's if you have a negative value, right, versus if you have a positive value. All right, so just be mindful of that. That situation in terms of the minutia of the variables themselves. Let's discuss levels of significance now. Levels of significance is symbolized by the Greek alpha symbol. All right, essentially, alpha values are otherwise known as the alpha numbers. Are known as the critical, otherwise known as cutoff values. All right. also used to determine two variable relationships. Right. But it does this by way of probability. Okay. So what you may see is one of two things. If you see a probability of 5%, that means %5 chance unrelated. If you see 1%, it means a 1% chance unrelated. It's kind of a backwards way of speaking, but you'll see what I mean in a moment. Hopefully that's not in the way. Okay. Just to add to this, if the R value that you calculated, and will be put into an absolute value, is greater than alpha. Remember, alpha numbers are critical values. All right. Then what you will do is assume yes, a correlation exists. Between two variables. If, on the other hand, the R value, again, put into absolute value symbols so you get just the magnitude that you're concerned with, is less than alpha, you assume no correlation exists between the variables. Okay? So basically, what you're going to see is a table. This is always the case in math, right? And in statistics especially, which we are grateful for. Show me where I put it. There we go. In this part of the handout, what you're going to be seeing is a table that looks like this. Notice at the top you see alpha, and then you see a decimal 0.05. Which if you wrote it in the style of a percentage would be what? 5%, right? And then you see adjacent to it a column of 0.01. which again in the style of a percentage would be 1%. Right? These are the critical values for the correlation coefficient of R. All right? These are your alpha that are at 5% unrelated. These are your alpha at 1% unrelated. Now think about what that is. Again, this is sort of a backwards way of speaking. If this says that there's a 5% chance that the two variables are unrelated, that means in theory that there's a 95% the balance that they are related. All right? But a person likes certitude, right? Especially in statistics, right? So a 99% chance, which correlates to 1 here, all right? 1% chance unrelated means 99% related. This would be pretty much predicting that the two things are in fact related, right? Using probabilities rather than just an R value. We're comparing R to critical values, okay? These R values that are given, just beware, you're going to read these for specific sample size, N. So if you, in the case of the last problem we had technically a sample size of 6, right? There were 6 data values, data points. So we would read the A value at the location of N equals 6. Right? Here is that table again, just to reaffirm that. Here is a critical value for both of these probabilities, all right, for 4 data points, for 5, for 6. We would read here at 6. And we'll come back to that. Now let's use the last example. All right. To get a feel for this. Okay. All right. If the R that we calculated was about 0.922, right, from example 1. Right, what we'll do is, using a sample size of N equals 6, right, let us read alpha at 5% level of significance. Okay. So the best way to do this is, maybe I'll just turn on the projector. There we go. I don't need the whole thing, so I'm just going to obscure part of it intentionally. Let's just consider this table here. So, hopefully this will be visible. at n, the sample size of 6, right? Here are the 5% and 1% levels of significance, right? 5% unrelated, 1% unrelated, which means 95% chance that they're related, 99% chance, all right? What is the relationship between this figure and the absolute value of 0.922? .811. What is their relationship? I don't know if that's visible. Might be a little bit easy to see, right? I'm just taking this figure from the critical values table, all right, and comparing it to the R value that we calculated. All right, would you say that this is greater or less, essentially? Right. Well, regardless of whether this was positive or negative, what you would get from an absolute value is 0.922 approximately, right? And the critical value that we're comparing to is this 0.811. Right? So the relationship would have to be greater in this orientation, right? And it is always the R value on the left side of the alpha value. So if the R is greater, and it is in this case, we can assume, yes, there's a correlation does exist, right, between the variables, with essentially a 95% certainty. Right, that they are unrelated, which is very good, obviously. Right. The ideal would be a little bit higher. We would be comparing, notice, a slightly higher number then. It still would fit in that if we used instead at 1%, and we use this figure here, 9.17 for 6 data values, you'd see that, look, 922 is greater still than 917. So at that point, we would have a 99% chance that they are in fact related, which is quite good. Okay. The larger the sample size, right, the smaller the value of R that is needed, right, to certify a relationship. Basically, more data is always better, right? It's true of pharmaceutical drugs, it's true of everything, statistics. More data is better. I'm going to just sort of walk you through the example that is example 2, and then we'll go back and do example 3. All right, get rid of this, it's a little bit distracting. Okay, here is the second problem that you might be a little distracted by. Let me turn this on. Alright, and erase some schmutz here and walk you through this. Try to emphasize some points here. Let's see. The amount of drug remaining in the bloodstream, right? To test the length of time that an infection-fighting drug stays in a person's bloodstream, a doctor gives 300 milligrams of the drug, I need that piece of information, to 10 people, 10 patients, right? Labeled 1 through 10 in the table below. Again, don't be bogged down by certain details. Once each hour for 10 hours, right? These are just coincidentally the 10 patients and the number of hours, unfortunately. Once each hour for 10 hours, a random one of the 10 patients, right, is selected and that person's blood is tested to determine the amount of drug remaining. What that means essentially is that the data that you see here, not that you should really dwell upon this too much, is that these potentially are different people. Okay? All right, the information is taken from different people as the experiment or the test proceeds. Okay? The results are shown as follows. Right? So, after an hour, right, random person is selected, and then the amount of drug in their bloodstream is measured, 250 milligrams. After 2 hours, all right, random person is selected, all right, and then 230 milligrams. All right, after 3 hours, all right, measured 200 milligrams. After 4 hours, 210. After 5, 140. And as you can see, it's generally going down. All right. Why would it go up in one case over here? Because we're technically using a different patient here. All right. It's not the same person. All right. All right. So here's what they ask us to do. All right. Determine a level of significance of 5% whether a correlation exists between the time elapsed, hours, and the amount of drug remaining milligrams. Right. Now, in order to do that, what would we have to do? It is implied this implies, right, we need an R value. Right, without explicitly stating it, right? Then we're going to compare, to alpha at 5%. Level of significance. Okay, so without driving you crazy, right? There is in fact a data table, all right, and you can see it actually in the problem here. I'm not going to make you do it again because it's a little bit cumbersome, but there is in fact a data table here that takes the data 1 hour, 250, 2 hours, 230, and so forth, all right? And goes through the trouble of calculating x squared, y squared, x times y, and then these sums. And then inputs them, you could see that. But what I think I should probably do is show you a little bit of a shortcut, all right? And that is involving a calculator at this point, all right? Rather than make you do it by hand, all right? And I don't mean just setting it up to divide. I mean that you get it to calculate an R value for you. Now in this case, I'm going to turn it on and clear out. Remember the process from a couple of weeks ago, right? I think that was this class, wasn't it? You guys had calculated averages, right? So we are familiar with this point that if you press stat var, right, you can get some pertinent information in here, right? But what we're going to have to do is rig this calculator so that it does 2 variable input. So let me just get out of here for a minute. All right, if you hit second and then data for stat, we're gonna first of all scroll over to where it says clear data and then hit enter, and that will erase any data that was in there. So you see blank x's and eventually blank y's as well. Clear out of here, please. Yes, it's a little redundant. Okay, so having done that, now what we're going to do is we're going to go back here and hit second data to get stat, and then now opt for 2 variable statistics. Right, we had been using 1 variable for averages, but now we need 2 variable. All right, and then hit enter. And now when you press data, what you're going to see is that there will be a blank X value, but as you scroll either left or right or down, there'll be a place to put Y's, right? So you do have to be careful, right? But if you take the data from this table that you see here, 1 and 250, right? 2 and 230 and so forth. What is in the lighter sort of, I don't know what color that would be. Cream color, I suppose. All right, this lighter cream color, this is X, this is Y. This is X, this is Y. X, Y, X, Y, all right? Time is the horizontal axis for this spread of data, and this is what it would look like. So we're going to pretend that those are the X's, all right? And the milligrams, amount that is in somebody's bloodstream, 250, say for this first one, that is the dependent or Y variable, all right? So we'll put these in tandem, 1, 250, 2, and 230, all right? It's a little bit temperamental, but I'll try to do it backwards here, all right? Go back up, all right? 1 hour for X value, scroll down, 250, all right, and then scroll down. Then at 2 hours, scroll down, put in 230, scroll down. At 3 hours, it's 200. You see, and keep proceeding until you do all 10 data values, right? So human revisits can, I'm just sort of flipping back and forth, and I don't want to make a mistake. Okay. 4 to 10. 5 for X, 140 for Y. 6 for X, 120 for Y. 7 for X, 210. 8, 100, 9, 90, and 10 is 85 milligrams. Now, just to scroll up to see that I've inputted everything correctly, here's 85 is for 10, 90 is 9 for X, 100 is 8, 210 for 7, 120 is 6, 140 is 5 hours, 210 is 4 hours, 200 is 3, 230 is 2, 250 is 1. Okay, so all of the data is now entered. So what we're going to do is now press StatVar here, and it will do the calculation of R even the letter regression, it will tell us. So StatVar, and it's not obvious because it's obscured, but notice that there's an arrow here. So we could scroll through this. Here's N as in the number of data values in tandem, the data points, so 10, naturally. I'm not sure what it's calculating an average of. But if you scroll past this, you'll see that it does some of what we would have done by brute force here. And on the very far right side, there's our regression, linear correlation coefficient, all right, R. So negative 0.87, all right, just as it was calculated by the example in the book, all right. So if this is what we assume now, that the R value is negative, approximately, because it's rounded, of course, 0.871 to give it 3 decimal places. That makes sense. If it's 0.8708, that would round to 1. All right. We're now going to compare to the alpha critical values at 5%. Right. N equals 10. Right. So we need to, although it's sideways in this case, I put it on the bottom of the page. Right. So you would have it here. At N, 10, right, you would be looking here at the critical values. right? And it's asking us for 5%. So the absolute value of negative 0.871 has what relationship to the critical value of, it's sideways, I'm sorry, but 0.632, right? If you took the absolute value of negative or positive, what is it going to give you naturally? It's going to give you just the magnitude distance from 0, so technically it's a positive, right? 0.871, which we will now compare to this value of 632, right? And analyze what the relationship is. So this is evidently greater. 0.8 is greater than 0.6 if we're just looking even at the 10th place, right? So we assume, yes, a correlation does exist. Right. Between essentially the amount of time and the amount of milligrams in somebody's bloodstream of some substance, some drug. Okay? In spite of it being negative, so don't worry about that. All right. Now, if you look at example 3, example 3 is asking us to take the data from example 1. Use the data in example 1, absent workers and defective parts problem, to find the equation of a line. All right, since we're dealing with linear relationships, it would be appropriate. That best fits the related data. What we're going to be calculating is essentially what is referred to as the line of best fit. Now, what I want to show you before I proceed is basically this. We did a lot of the work already, but let me pull this up. All right. In the packet referring to this formula. Get rid of that for a moment, because it's a little distracting. In the subject of regression, right, we can calculate a line of best fit. And again, what this is referring to is if you have data that are not perfectly in alignment, what can be calculated is a line of best fit, right? And that takes into consideration the distance of any of the values to this potentially perfect best fitting line here. You can see that it varies. In order to calculate that brute force, all right, we would use a similar looking formula. It's not exactly the same. It has, the top is the same basically, but the bottom is only parts that are the same to calculate the slope. All right? And similarly, we could use this formula to calculate the Y-intercept. Right, of this hypothetical ideal line that would fit as best as it possibly could between this random squiggle. Right? If the data kind of jumps around like this, right, we want a line that basically describes it ideally. Right? That's the line of best fit. Right, just beware, the formulas are very similar looking to the linear regression coefficient, but they're not exactly the same. The bottom is different. Okay, so if we were going to basically borrow some stuff from example 1, this is example 3. What we're working on, but we're borrowing information from example 1. Remember that from before, right? The very top of the linear coefficient, linear correlation coefficient was what number? Right? it was the number 520, right? Was the very tippy top. Right? When we were using that formula, we had 520 on top. That happens to be the same guts that you see here in this formula for slope. Right? So when we're calculating slope instead, we're going to borrow that figure. Okay. As for the bottom, this is the inside guts of the first radical. In the regression the linear correlation coefficient formula. So that would be 161 here, right? Outside of a radical, right? Because it's not part of this formula. Right? What do you get if you divide 520 and 161? You get a slope that is approximately, because of the nature of this, decimal, 3.23. Right. If you calculated it for B, borrowing some of the parts here, which you notice that this formula is dependent upon this M value. So in this, if you placed 3.23 and then some other pieces that we're borrowing, this would still be 6 again. All right. The B value that you would get is approximately 8.52, right? Which, if you're going to take this and write this as the line equation, for the sake of calling it best fit, something that ideally describes the data, right, which may have been measured poorly. All right. We would have this. We would take the figure 3.23, attach an X to it in the model, and then the Y-intercept value, which is normally a whole number, right? But it's a decimal in this case, so 8.52. Now, let me show you something else. Right? I'm going to have to clear out the data from before, but if you don't feel like going through the intricate work of figuring out this value or this value, I wouldn't fault you really. Part of the reason we invented software, humans, is to simplify our lives. So what I'm going to do is I'm going to input the data from example 1 to answer this question of 3. But I'm going to go back to my calculator and clear it, and then go to second and then data again. Choose 2 variable statistics, make sure that it's still that, and then input the data values from example 1. Right? Which means, to flip around a lot, I'm going to type this down. For X, I'm going to use 3. For Y, I'm going to use 15. Remember, this is data taken from example 1 for the purposes of answering example 3. For 2, it's 5 and then 22. And I'll do it 0 and then 7. 1 and then 12. 2 and then 20. 6 and then 30. And just to show you, these are all example 1 data points. 36, 22, this is reading it backwards of course. 12, 1, 7, 0, 22, 5, and 15, 3. Right? Those are the X's, those are the Y's. Now we're going to cheat and get the calculator to basically figure out the slope and the Y-intercept for us using these data values instead. So we're going to hit stat var and then scroll all the way to the end. Now you see what we did before was we used it to get the linear correlation coefficient, but what we can do is then read these all right, A and B. A and B are the slope and the y-intercept. So let me just make sure that that is clear. Right? Most of the time, math purists will just write the line equation as y equals mx plus b. Right? But some textbooks, instead of calling this m, they will call this a. Right? Others still will use like subscripts, which to me is like the ultimate in just like, you're really going crazy, guys. Not gonna work with that stuff. So on your calculator, right, look for A, and then look for B, and realize that A is the slope, right, and B is still the y-intercept, which is weirdly labeled to begin with. Anyhow, the A value, which is the M value, is still, according to our calculator, what figure? Initially we had, I cheated a little bit, but 3.23 to begin with. Let's see what the calculator says. All right, 3.229. All right, so if you rounded it, again, 3.23. All right, for slope. If you scroll over to B, 8.2, no, pardon me, 8.515, so 8.52, right? And that's very handy, right? Don't have to keep reinventing the wheel every time. So anyhow, we get the same information, we just have to round. So this is about 3.23, the B value, 8.52, and then you can insert them in the equation. Okay, there and there, the model. All right. Now, the second part of this question was, let's go back here. Graph the equation of a line of best fit on the scatter diagram that illustrates the set of bivariant data. They want you to basically, in this case, let me erase the gobbledygook. They want you to take the scatter plot and superimpose that line on it. And what you will see will happen in this case is that it'll be pretty much right down the middle of it. Now, what you could do, if you're really adventurous, is start with this piece of graph paper. All right, I'm going to do it brute force just to illustrate one time, but here's a piece of graph paper that I prepped for this purpose. All right. And I'll show you how to label this and divvy it up here. You don't, like normally you would use a graphing calculator if you had a situation like this, but here's a piece of blank graphing paper, all right, that I have chopped up into essentially quadrant 1, right? If we took the data, from example 1, I have to keep flipping back and forth, I hate this, but if I took these data values, 3, 15, 5, 22, and so forth, and then basically take where these dots would be and put them on a piece of graph paper like this, I'm going to then superimpose the line of best fit on it to illustrate the relationship here. So here's how I would decide to chop this up, right? Because this is in landscape rather than in portrait, right, it's favoring being wider this way rather than longer this way. And our maximum, if this is a y-axis, and this is an x-axis, otherwise known as the dependent variable and the independent variable. In the context of example 1, these are absent workers. And these are defective parts. Right. If the minimum number of defective parts is something like what is it, 7? Look at this table again for example 1. The lowest number here is 7 for defective parts. Right? The highest one is 30. Let me see if I can chop this up so that it ends pretty much right where it should be. Right? I'm going to start with 0 in both cases. You don't always have to do that for the vertical axis here. Let's say that I counted by, let's see, 5s or something. I won't go every increment here. I'll just go up every 3. Right? The increments that are chopped up this way, the breadth of them, can be different than they are horizontally as well. So let's say that from here to here is 0 to 5. Right? Up another 3 is 10. Up another 3 is 15. Up another 3 is 20. Up another 3 is 25. Right? And up another 3 is 30. Right? Based upon the graph paper and the maximum, right? Where the minimum was is not quite 0, it's 7, but I wanted it to look like this, so it fits fairly well, right? And this is how wide each of these increments is, 3 blocks tall. Doesn't matter that it is that not 1 to 1, okay? On the X scale, right? In which case I would definitely start at 0, all right? The minimum is coincidentally 0. But the maximum is 6. So I'm going to borrow from the textbook and try to chop it up this way, all right, to make it fit rather nicely. And you can only do this by experimentation, all right. I'm going to break it up into 6 increments this way, all right. For, again, that correlates to not days, really. It correlates to number of people absent, all right. Based upon how it is wide this way, and I want to start at 0 and go to 6. How did I break this up? I went every 5, right? 1, 2, 3, 4, 5. 1, 1, 2, 3, 4, 5. 2, 1, 2, 3, 4, 5. 3, 1, 2, 3, 4, 5. 4, 2, 3, 4, 5. 5, 1, 2, 3, 4, 5. 6. All right. That is purely to make it nicely fit. It doesn't have to be exactly 5 blocks, 5 blocks, 5 blocks this way. It could have been a little bit smaller. It could have been 1 to 1, you know. But I'm trying to make it look aesthetically pleasing. That's the only reason. And I'm deviating. I'm using 5 this way for an increment and 3 this way for an increment, just to show you that they don't have to be perfect. All right? They don't have to be 1 to 1. All right? Anyhow, if I now finally, all right, take the time to graph these as though they were X's and Y's in tandem. At the location of 3 for X, I'm going to put a dot at 15 for Y. So, 3 people absent. I'm going to go up to where it's 15 and put a dot here. Okay. This is a little bit tricky, I'll have to estimate. 5 people absent, 22. Put a dot at the height of 22. So 5, and here's 20. So I'm just going to draw a line here for my own sake and then erase it. It's basically in the vicinity of these 2 lines. All right. This is 20. This is 25. All right. Because of the way that I broke it up into 3. All right. Let me figure out what it is exactly halfway, which would be there. All right. Halfway from 20 to 25 would be 22.5, right? So just underneath this would be the line of the point of 22. So if that's right smack in the middle, I'm going to put a dot approximately there. That's the beauty of having grid lines. It makes it a little bit easier when you're doing that. Perhaps if I were a little bit better and I had a little bit taller piece of paper and I incremented this a little bit nicer, as long as I'm consistent, these are all 3s, these are all 5s increments, all right, I would have made it easier on myself to guess, but it wasn't perfect to begin with, so I don't worry too much. All right, at 0, 7, 7.5 would be right in between 5 and 10. So just underneath it is basically a dot of 0, 7. Okay. At 1, it's about 12. Right. So if this is 12.5, right, it's exactly halfway between 15 and 10. It would be just underneath that, up to here. So I have a dot just approximately there. And at 2, it's 20. 2, this one's easy, right? It's right on the grid lines. And lastly, for 6, it's 30, so that is also fairly easy. 6 is 30. So there. All right. This simulates the graph that we have in our book, right? All right. There's that point, that point, that point, that point, and that point. And it's a little bit zigzaggy, right? It's not perfect line, right? Which could mean not enough data, right? Or the instruments that were used in the experiment, which was just counting people really, was and something more complicated. All right, it would not. They were not measured or calibrated well. Right. Anyhow, if we take the line that we have established according to calculations from statistics, we can superimpose it in here. All right, that was really the whole point of example 3. All right, now you could just take this exactly as you see it and insert it right in here. Just use the slope. Right? It's so much up over so much to the right or left. Up, down, right or left. This figure. And then this is the coordinate 0, 8.52. Right? Or you could try to flesh out the graph using these figures. Right? Which is the way that the book went about the process. Like for instance, you notice that for 4 employees, there was no data. So let's say that we ran the calculation using 4 here, right? So I'll do it over here. All right. I think green is not going to show up, so I'll use black. I'm going to do some extra points. Extra points to flesh out the picture. Right? If I stick a 4 in place of x here, then do the multiplication. 4 times 3.23, it's a rounded number, of course, so it's not going to be perfect. All right, plus 8.52, all right, you would get this coordinate. 4 for the input, all right, math speak again, and then something like 21.44, all right. Okay, so we'll take this extra point in putting a 4 here, right, and put a dot. I'll put it in red just to contrast, right? At the location of 4, we're going to go to, it's almost 21 and a half, right? Let's see. Uh-oh, don't go to sleep on me now. Right. See, I'm boring even my computer, all right? Here's 22.5. Because of the weirdo way that I have incremented it. No. 5 divided by 3. This is like 21.6 repeating. So I'm going to just grab that line, okay? This first line above 20 is 21 2/3, so 21.6 repeating. So at the location of 4, I'm going to put a dot approximately there. Okay. Let me do another one. I need a minimum of 2 dots really to accomplish this. Let's see. Use a small number because it will make it easier for math. Right? If you use 2 as the input variable for x, right? Then where would you have a point? You would have a point at 14.98, something like that. Right, so approximately 15. This would be approximately 15. The location of 2, go to 15. And we have a point here just instead. I know that we had data value for 2 already, but I need at least another point. All right. Now, the book goes ahead and does it for 6 as well, which is no sin. More data is better, but 2 is sufficient. If you use 6, what would you get in the calculation? You get 27.90, looks like. All right, sticking a 6 in here in our formula. All right, which is about 28. All right. At the location of 6, you can stick in another dot just underneath 30 here. You'd have something like just about there. All right. Anyhow, you then take a ruler and connect the dots. All right. And just because this is cumbersome, I'm going to take the cap rule first. All right. So, connect the dots as nicely as you can, especially those reliable 2 there. And overextend the line. Frick. It slipped. It's because I'm like, I'm like a mouse, if you can imagine it, wielding a human-sized ruler. There you have it. Right. And you could reinterpolate it in this case. We got a data point that was in between. And you could extrapolate, which is you could overextend the line past the data values to make predictions beyond 6 people, for 7 people, for 8 people. That's a visual aid, right? Anyhow, this is known as the line of best fit. All right. And it would be described by this algebraic equation. Y is 3.23x plus 8.52. Right? Historically, our teachers would tell us, hey, listen, you better label this. So you write the equation that describes the line along it. Okay? All it is basically superimposing over the data, over the scatter plot, right, which is in blue. Okay, so that's pretty cool, right? Just make sure that we did everything here. Yeah, okay. For example 4, and go back here. Example 4 is, okay. Determine the equation of a line of best fit between the time elapsed and the amount of drug. This is referring back to example 2. Right? If the average person is given 300 milligrams of the drug, how much will remain in the bloodstream after 5 hours? Okay. Let me turn off my projector because we don't actually have to draw anything in this case. We just need to get the data. All right. Pull that back, turn the light back on, turn and erase this. Okay. Again, in this case, not to reinvent the wheel, I would use your calculator. Ideally, it is the type required for the class, the TI-30X2S, all right, to calculate your slope and your Y-intercept. Okay, so in the case of example 4 here, all right, it's taking data from example 2, about the drugs, all right, and we want to calculate the line of best fit. So we need to know the mx plus b, right? We need to know the a and the b value from a calculator. Right. If you take the data, I think I probably erased it by now. Yeah, I definitely did. I'll do that really quickly. I'll input the data and then get it to spit out this information again. All right, to go through this exercise, remember you got to clear out stuff. So you hit second and then data to erase what was in there. Scroll over, clear. Make sure that you are choosing second data, two variable statistics. So you're entering an X and a Y. And then go through the process of taking data from example 2 again. All right. So 1, 250. And then 2 and 230. And then 3 and 200 again. 4 and 210. 5 and 140. 6 and 120. 7 and 210. 8 and 100. 9 and 90. 10 and 85. So let me just verify. Yep. The tedium is just in making sure everything is set correctly. 5 to 10. Yeah, looks good. All right, so with the data now inputted for X's and Y's respectively, hit stat var, right? And again, scroll over to the very end, and we'll see that we have an A value and a B value, that's slope and Y-intercept respectively. And here is what we have, right, for A. The A value is a negative for the slope. So negative 18.09. High degree of precision there, very good. And the B value yike. All right. Am I reading it backwards? 263, yes. Because this is milligrams. So this is part A, right? And part B is asking you to basically run a calculation using this model, right? So it's more algebraic than it is graphical, all right? Essentially, how much after 5 hours? How many milligrams of the drug still present in a person's bloodstream after 5 hours? As long as we understand that X is representative of hours, right? You could just type in negative 18.09 times 5, add 263, and what you would get is this, 172 rather, 0.55 milligrams remain. Okay? And that's it. It takes a little bit of getting used to, but that's the reason why I make people do, or encourage people to do, brute force, right? If you get deep in the weeds of the math, it becomes more familiar naturally. The more you do it, the longer you stay. So, more is better when it comes to learning something. Repetition. Okay, so we're basically done. All right, for homework, what you want to do is section 12.6 in my lab. All right, and then you're basically good. Now, if you noticed on the calendar, test number 3 is on Wednesday. So I'm going to mail you as I had the last 2 times, and I just want to, I'll shoot a video giving you the solutions. I want you to spend the time, as always, doing your homework, please. Especially this, because it's involved, all right? Don't Don't gloss over it, all right? You won't learn anything if you just kind of try to do it in 5 minutes. All right, take your time, all right? Even if it is Wednesday, all right? On Wednesday, all right, I'll mail you test number 3. Okay, and then shoot a video for solutions. All right, just make sure, all right, that you're finishing up, especially taking the time with 12.5 and 12.6. 12.5, remember, was 2 sections. Okay? All right, I'll see you again on Wednesday. Be careful out there.